Now, rate laws usually involve, reactions usually involve more than one reactant. Only for a decomposition reaction do you only have one reactant. So anyway, for the ones where you have A plus B going to some products, the rate is your reaction coefficient, K, A raised to the mth power and B to the nth power. And these M and N, remember, are not the coefficients in front of A and B, but instead is the order with respect to A, and N is the order with respect to B. And the overall order of the reaction is M plus N. Now, the order with respect to a reactant indicates the dependence of a reaction rate on the concentration of that particular reactant. The overall order gives an understanding of how all the reactants contribute to the reaction rate. It also dictates the units of the rate constant for that reaction. One way to determine the rate law of a reaction is to measure the initial rate, that is, the rate at the time 0. If the initial rate is measured with a number of different initial reaction concentrations, then the rate law can be determined. This involves quite a bit of work. The order with respect to a particular reactant can be determined by varying its initial concentration while holding the initial concentration of the other reactants constant. So essentially in your experiment you are measuring the initial rate of each of the two different concentrations. And the change in rate is then a direct result of the reactant which is changed in the concentration. The order with respect to that reactant can then be calculated. And you have to again keep repeating this whole process for every single reactant. Let's talk about integrated rate laws. So far we've talked about a product concentration relationship where a reactant, goes to products and it has a rate K, A to the nth power. The rate law can be integrated with respect to time to produce a concentration time relationship known as the integrated rate law. This relationship depends on the order of the reaction, 0th order, 1st order, 2nd order. And this is where that factor M or N or whatever comes into this equation. A new term, the half-life, now needs to be introduced. For a first order reaction of the type A going to products, that is a decomposition reaction, where the rate is Ka, integration with respect to time gives you the log of the initial concentration of A divided by the concentration of A at some time later equals that rate constant times time. Okay, and remember, what's in brackets there is the concentration at that particular time of the reactant A. So the linear form of the first order integrated rate law is log of A0 over AT equals KT. You can put this into an equation. Log of A at time t equals minus KT plus the log of A0. Or in other words, the form that you get is of this variety right here. Y equals mx, where m is going to be the slope. So that's how you get this K. You look at the slope of this, and it will be this value right here. This term right here becomes your intercept. Okay? So this is plotted on the x-axis, on the y-axis. This is plotted on the x-axis. The slope is this, and the y-intercept is this factor right here. Note that when using all the integrated rate laws, you have this term becomes this right here. The amount of reactant does not always need to be expressed in molarity, as the equation implies. The amount can be expressed in mass, grams, all of these other things, because essentially what you're doing is you're looking at the slope here. You're not looking at what these values are in and of themselves. As long as these are both consistent in terms of either mass or moles or partial pressure or whatever, you will have a very good way of determining what your rate constant is. For example, on this right here, you have the time over here, and here you have the log of the concentration of peroxide. And this shows a linear decomposition with this. Okay, this indicates that this is a first order reaction. Now here, this is not a straight line. So for whatever material this is that's decomposing, this is not going according to a first order reaction. These two graphs show first and second order plots for the dimerization of C4H6, right? This is essentially this is ethane. The linear trend of the second order plot that is over here indicates this follows second order. This is 1 over that concentration. This is strictly the log of this one right here. Okay? So when you're looking at this one right here, if it's the log of this, as we saw from that equation, and it's not linear, this right here indicates it is not first order. If you can do the 1 over that concentration with respect to time and have it linear in this direction, that means it's following second order kinetics. Okay? The second order is the reciprocal function correlated with time. So it's 1 over the concentration times time, giving you a linear relationship. It means that it's a second order. And again, the slope of this line is your K value. Here you have two different decompositions. This is the decomposition of tungsten. This is the decomposition of SiO2. This is quartz. And this right here is not first order. Okay, well, this is a decomposition on two different surfaces. So the decomposition on the tungsten surface is a 0th order, and the decomposition on this surface is a reaction that's first order. The half-life of a reaction is the time it takes for 1/2 of a given amount of reactant to be consumed. For the first order reaction, the half-life is T is 1/2 of the initial concentration at time T. Solving for that T in this equation right here gives you the log of 2 over K. So the half-life, how long it takes for it to decompose into half of its value, that time equals 0.693 divided by the rate constant. So you can also determine this K value here by essentially multiplying, dividing 0.693 by the half-life, the time it takes for it to go down to half its value. Note that for a first order reaction, the half-life is independent of the initial concentration. There's no concentration in here. This is only dependent upon, it's only a relationship between K and this, two different constants. The symbolism, the decomposition of hydrogen peroxide into water at 40 degrees is illustrated by the intensity of the color. And intensity of color is another way of measuring the concentration. So when you look at this, after 6 hours, it's half as light. It decreases to half its concentration again at 12 hours, another 6 hours, and then 24 hours. Okay? So the second order reaction rate is the rate equals Ka times the concentration squared. So integrating that with respect to time, and you don't have to worry about doing that. This is what it actually works out to be, is where we get this half-life of 1 over the concentration equals Kt, 1 over the initial concentration. And that's when we get this type of relationship right here. And that ends up being a curve that goes down in this direction, right? From what our initial value is, because it's the inverse. of this that's related to that time. So it's a way of getting the reaction constant here from the curve, and then from that we can then calculate what this T1/2 is. And this does depend upon what that initial concentration is. For a 0th order reaction, A going to the products of the rate equals K times A, the initial concentration, equals K. So here, the integration with respect to time gives us this value. The concentration is minus KT plus this initial concentration. So the T1/2 is this right here, and so the 0th order does depend upon that initial concentration of the reactant. Now, one of the things before I mention all of those different the collision theory is that on table 12.2 in your book, you have a summary of the rate laws for 0, 1st, and 2nd order reactions. Okay, so that's a very good reference for you to have to essentially print out, and so to show you that if you have a given relationship and plotting the initial concentration and the change in concentration over a matter of time, you can determine exactly what rate constant you are working with just from the shape of the curve and the direction of the slope. Now, as far as collision theory, we talked about the reactants must collide in order to react with each other. So the rate of reaction is proportional to the rate of these reactant collisions taking place. That's our first postulate. A postulate is just sort of a rule of thumb in this matter. So why does every collision not lead to a reaction? First of all, molecules must be oriented properly when they collide. They also must have the proper energy. Molecules must also have adequate kinetic energy to react. The kinetic energy supplied must be high enough to break the chemical bonds. Molecules with kinetic energy too small just bounce off each other and don't react. This required energy is what we call activation energy. This is the minimum energy necessary to form a product during a collision between reactants. So in the first example here, first of all, you have the no reaction because this isn't the proper orientation. Now you have carbon and oxygen lined up when they collide. You also have sufficient energy here. So now you have carbon monoxide being formed into carbon dioxide. Okay, so this illustrations are two collisions that might take place between carbon monoxide and oxygen, and the orientation is very critical. Otherwise, you can't get the carbon dioxide. There's such a thing as a transition state model. And scientists and chemists spend a lot of time looking at why certain reactions take place. And they postulate different reaction energy diagrams. The potential energy is plotted on the y-axis. The reaction path, or extent of reaction, is plotted on the x-axis. The reactants form an intermediate called an activated complex. The state of the system at the activated complex is called a transition state. So we've talked about the concentration rate dependence, the concentration time relationship. Now we need to look at the temperature rate relationship. Reaction rate ordinarily increases with temperature. To cook food more quickly, you raise the oven temperature. To slow the reactions that lead to food spoilage, you put it in the refrigerator, or to really slow it down, you put it in the freezer. Here is an example of something going through a transition state. You have your initial energy of the two different reactants. You have your final reaction, final energy of the system when they become C plus D. This is a double replacement reaction. And this starts off with this energy. It must have achieve a certain transition state here for the orientation as they collide. Once it does that, the new molecules are much more energy favorable, and so they come down all the way to this level right here. And we'll stop for there.